Different orbitals, and remember orbitals are these regions in which we're most likely to find an electron in an atom. Each individual electron has its own different electrons are in different orbitals which have different shapes that depend on where the electron waves constructively interfere or not. And so the orbital shapes, we have different ways to describe them. And so we'll use a series of letters for them. And so S is one orbital shape, P is another orbital shape, D is another orbital shape, then F, then G, H. At that point, they keep going, but they go on by the letters of the alphabet, so H, I, J, K, and so on and so forth. So these orbital shapes, let's take a look at them. So the first one up here is an S orbital. And so S orbital really has just one shape. It's a sphere. In fact, that's what S stands for, is spherical. And so that one shape that it can be is just that sphere right here. The p orbital, you can see that there is a p down here along each one of these. There are three different shapes of orbital that are in the particular p configuration of orbitals. And so if you look at it, you can sort of see that it's got these sort of two bean type shapes that are sort of skewered by an axis. So we have the bean shape that's skewered by the x-axis, the bean shape that's skewered by the z-axis, and the bean shape that's skewered by the y-axis. And so we have these same shapes, but they're just all perpendicular to each other, sort of lined up with a different axis. And so that's an orbital shape for p orbitals. The next orbital we said was a d orbital. So the d orbital has even more, not just 3 different configurations, it's got 5 different configurations. And so you can see the pictures of those there. The green one at the bottom, that's your f orbital. So there are, let's see, 1, 2, 3, 4, 5, 6, 7 different f orbitals that exist. Once again, all different shapes. Some are just different orientations of each other. If you look at this one right here and this one right here, you can see they look a lot alike. The only difference is that they're flipped around from each other. But then you have other ones that really don't have anything that's like them anywhere else. And so this guy right here is sort of with the 2 rings and the 2 sort of ball-shaped regions up there. And so what we'd be saying for each of these is if we had an electron that was in this orbital, then it would have a 90% chance of being in that double ring, double sphere shaped region right there, and only have a 10% chance of being outside that region. Or if we had a case of an electron that was in this s orbital right here, that it had a 90% chance of being in that spherical region, only a 10% chance of being outside that spherical region. And so that's sort of an example of what shapes these have. Just so that you're aware of sort of how these orbitals look if you have them around the atom here. So let's do some more terminology. So a shell in an atom is another term for an atomic energy level. So if you had an electron in the second energy level, you could also say that it's in the second shell. So just a different way of saying what we've used before with energy levels. Now each shell is made up of one or more subshells. And a subshell is an energy level combined with a type of orbital shape, such as 1s or 3p. And so if we said that we had sort of a 1s subshell, that tells you that its first energy level, that's the 1, and then what's the shape of the orbital that's within it? Well, it's s. So we look back over to our previous page right here, and so this is s right here. So it would be first energy level, it has a shape like that. Now if it were 2s right here, 2s, then that would indicate its second energy level, but the shape of the orbital still looks like this guy right here. It's still that spherical shape. Okay? So first energy level just has one subshell. It's only the 1s. The second energy level has 2 subshells, both the 2s and the 2p. And so second energy level, you could find electrons in that spherical shape or in any one of these 3, but you would never find a second energy level electron in any of the d's or any of the f's or anything like that. It only could be in those 2 possibilities. Third energy level, though, has 3 subshells, 3s, 3p, 3d. So the third energy level, you could find that third energy level electron in the s orbital or in one of the p orbitals or in any of the d orbitals in here. So those are the different places where those electrons could be in each shell or each energy level. So each subshell has one or more orbitals based on the type of orbital shape. So let's get a little more detail on this. So each subshell has one or more orbitals, basically set on the orbital shape. All s subshells have just one orbital. We saw that right here, that s only has one possible orbital. All p's, so if you've had a 2p or a 3p or a 4p subshell, they all have 3 orbitals because you look at the p, how many's it got? 1, 2, 3. All Ds have 5. 1, 2, 3, 4, 5 right here. So if someone said that, hey, we have an electron that it is in the 7D subshell, we said how many orbitals are in the 7D subshell? Well, it's a D subshell. There have to be 1, 2, 3, 4, 5. That's the only possibility. All F subshells, no matter what they are. So if I said someone had 10F, you're never going to run into 10F, but if you ever did, how many orbitals does it have? It has 7. 1, 2, 3, 4, 5, 6, 7. Now, if you notice, there's a pattern here. We said the order was S, P, D, F, G, H, I, J, K, on like that. Look at the numbers. 1, 3, 5, 7, 9. They're odd numbers. So even though I didn't put it down here, so FGH is the next orbital. How many, or is the next subshell that you could have here? You'd have like a 7H or something like that. How many orbitals would it have? So if you had the H here, it would have to have 11 orbitals. So that's our first thing we know here. Each subshell has one or more orbitals based on its shape. And so you look at the letter, and that tells you how many orbitals are in that subshell. Now, each orbital holds exactly 2 electrons. So if you had, like, say, the 1s right here, we know it's the shape, we know its first energy level, and the question is, how many electrons are in there? In this particular one right here, the answer is 2, because each orbital holds 2. Now, let's suppose you had a 4p subshell. Well, if it's 4p subshell, it's going to hold a total of 6 electrons. How do we know that? Well, we first look at the subshell type. It's a p, right? How many orbitals are in a p? P is right here, right? It has 1, 2, 3 orbitals. So there are 3 orbitals in any p subshell. We know that's true. Each orbital holds 2 electrons, and so 3 subshells times 2 electrons each gives us 6. If instead of that, let's suppose that we said, hey, let's look at this 10F. How many electrons are in the 10F subshell? Well, you'd say it's F. So since it's an F orbital type, we said all Fs have 7 orbitals. So the 10F would have 7 orbitals. Each orbital holds 2 electrons. So we multiply that out. There would have to be 14 electrons in the 10F subshell. So far we're just sort of figuring out how do we know what subshells there are, what shells there are, how many orbitals are in each one, but still it's like, how do we put this together? Well, let's start taking a look at the particulars here. So shell number 1 has just one subshell, just the 1s. S orbitals only have 1 orbital in them, so 1s subshell, any S subshell would only have 1 orbital in it. And each orbital holds 2 electrons, so there must be 2 electrons in the first energy level, in the first shell. We know that just based on what we have there. Second energy level, we said there were 2 subshells, a 2s and a 2p. Well, all s's have just 1 orbital, and so 2 electrons per orbital gives you 2 electrons there. All p subshells have 3 orbitals. 3 orbitals times 2 electrons gives us a total of 6 electrons. So if someone asked you how many electrons are in the second energy level, you'd say, well, it's got 2 subshells, 2s, which has 2 electrons, 2p, which has 6 electrons, so it has a total of 8 electrons in the second energy level. What about the third energy level? How many electrons could it hold? Well, 3s, an s orbital, an s subshell has 1 orbital, and so 2 electrons gives per orbital gives us a total of 2. A p subshell, any p subshell, has 3 orbitals, and so 3 times 2 is 6, so we have 6 right there. A d orbital, so remember that it goes, you know, spd, it goes up 1, 3, 5, and so there must be 5 orbitals in the 3d subshell. 5 orbitals, 2 electrons per each orbital gives us a total of 10. So how many electrons are in the third energy level? 2 plus 6 is 8, plus 10 is 18. And so on and so forth. You can see the same thing for the fourth energy level. It has an S, a 4P, a 4D, and a 4F. You notice it adds up. First energy level only S, second energy level S and P, third S, P, and D, fourth S, P, D, and F. Fifth energy level would have S, P, D, F, and G. And then we can once again, based on what the subshell type is, whether it's an S or a P or a D, figure out how many orbitals are in each subshell, and then from that figure out how many electrons are in each subshell. So, now that we know about what these subshells are, how do we know when electrons go in which subshell? Because we haven't talked about that. So we do already know this. Electrons will want to go into the lowest available energy level that they can. Remember, they're always trying to end up with that lowest possible energy. And the same thing is going to be true about subshells. And so this is called the Aufbau principle. Electrons will go into the subshells that result in the lowest total energy for that particular number of electrons added. So if I add one electron to an atom, say hydrogen, then that electron will go into the lowest energy subshell, which is the 1s subshell. First energy level, and there's only one orbital that's in that, and so that would be, you know, that s, which just has one, and so it would have to go in the 1s subshell. Okay? If I had 2 electrons, well, they would both go into the 1s. Okay? If I had 3 electrons, 2 of them would go into the 1s, but the 1s only holds 2, so the next electron would have to go into the next lowest subshell. The next lowest subshell is the 2s. And so we don't know why that is yet, but that's sort of how it works. Electrons will always go into the lowest subshells they can. So electrons will always fill up the lowest energy subshell first. Then when that's filled, they'll fill up the next lowest energy subshell. Then when that one's filled, they'll fill up the next lowest energy subshell. They will build up, which is what the word Aufbau means in German. It means to build up or to construct. It'll build up the atom until all the electrons are in the subshell. So it fills the lowest energy ones first. When that's filled, it fills up the next lowest energy subshell. When that one's filled, it fills up the next lowest energy subshell. And this should sound familiar to you because this is the same way that we talked about that the energy levels worked. When the lowest energy level is filled, then it goes up the next one. Only now it's not just true about energy levels, it's also true about subshells. And so how do we know which subshells have the lowest energy? We said it fills up the lowest subshells first, but we don't know which ones those are. So a couple ways to figure this out. So on the left-hand side here, I have a diagram that shows you the energies of the different subshells. So in this particular case, you can see the S's are right here. Here are the P's. Here are the D's. Here's the 1F that it has here. Each circle represents an orbital. So you can see the S has one orbital, the P has 3 orbitals, the D has 1, 2, 3, 4, 5, the F has 1, 2, 3, 4, 5, 6, 7, just like we said. And this y-axis here is the energy increasing as we go up. So you can see that the lowest energy subshell is right down here, is the 1s. And then after that, what's next? The next lowest energy subshell is this one right here, which is the 2s. I know it's a little hard to combine those together, but it's the 2s right there. But then what's the next lowest energy? The next lowest energy is that one right there, the 2p. Well, what's the next lowest energy? This guy right here, the 3s, then the 3p, then the 4s, then now this guy right here, the 3d. Keep going up in energy, filling low to high. After the 3d is filled, then it'll go up to the 4p. After the 4p, it would be the 5s, and then the 4d, and then the 5p, and then the 5s. And then just slightly above the 5s is the 4f, and above the 4f, the 5d, then the 6p, and on. But you're like, how am I ever going to remember this? This seems really complex. Well, there's a nice little trick to it. And so that's what we see on the right side. If you notice, what we've got here is we have our energy levels. First, second, third, fourth, fifth, and sixth. And then next to each one, it writes out the subshells that are in that. First energy level just has one, just 1s. Second energy level has 2s and 2p. Third energy level, 3s, 3p, 3d. Fourth, 4s, 4p, 4d, 4f, and so on and so forth. If you basically go down this line diagonally, go through this list diagonally, like the way the red arrows are showing, it'll tell you the order from low energy to high energy. And so the first one it goes through is the 1s. So that means the 1s has the lowest energy subshell. Now we go diagonally next. What's the next one? 2s. So 2s is next. What's the next lowest energy? It goes this way, so it would be 2p, then 3s, then 3p, then 4s, then 3d, 4p, 5s, then 4d, 5p, 6s. And that's the order, because you notice this is the same order that we have over here on the left side. 1s, 2s, 2p, 3s. We have 1s, 2s, 2p, 3s. And then over here you can see it should be next 3p, 4s, 3d. And sure enough, it's 3p, 4s, 3d. So you can see how we get the same order that way. So if you know how to do this little trick right here, you can always figure out which subshells have the lowest energy and which subshells have a higher energy. There's another way to do this. Compare it with the periodic table. So we said that electrons first go into the 1s, then they go into the 2s, then into the 2p. So if we look at a periodic table, let's suppose that we have just one electron, hydrogen. Would be the atom that just has one electron. So hydrogen's right here. If we put one electron into that, then that electron would have to go into that first subshell, the 1s, right? Because we said it was 1s, then 2s, and 2p were the order that we got here. And so Helium would have 2 electrons. So they would have 2 electrons in the 1s, so 1 for hydrogen, 1 for helium. Now you'll notice on here it has this labeled 1s. It says this is the s block because this little section right here has only 2 spaces across before it ends, that particular block right there. The reason why is because whenever you have atoms that basically you're filling up the electrons, these 2 spots correspond to putting electrons into an S subshell. And so you can see this, the 1s is hydrogen and helium. The 2s are these guys here, the 3s, the 4s, the 5s, just like we've talked about. So after we fill up the 1s, we would next fill up the 2s. And then where do we go after that? So that's, this is lithium and beryllium. Look at the periodic table. You can pause it if you want to get yours out. But after that is going to be boron, which is right here. Well, where is boron? It's in this section right here, which it labels as being the p block. So this section is where, as you add new electrons, you're filling up p suborbitals. And so, in fact, for this one, it's the 2p. And so, sure enough, after you fill up the 1s and the 2s, you next go to what? The 2p. And after you fill up the 2p, where do you go next? Down to here, to the 3s. And sure enough, after you get to 2p, what's next? 3s, right there. And the order on the periodic table, if you basically follow the elements and follow the atomic numbers on the elements, also will tell you what order that the subshells fill up. In reality, it goes the other way. Because of the fact that the subshells fill up in the order that you see here, is the reason why the periodic table is shaped the way it is that it fills up the 1s first, and so it has this little column of 2. Really, it's the 1 plus the helium that sort of goes in here. And then the next one is a column of 2 because it fills up a 2s. But then it goes a column of how many? 1, 2, 3, 4, 5, 6. Why is it 6? Because p subshells have 3 orbitals, and each orbital has 2 electrons for a total of 6 that fit in it. And then once you've got that 6 filled up, it can't go in the p orbital anymore. It has to go to the next lowest energy subshell, which is the 3s. And that's got 1, 2 spots. And once the 3s is filled up, we look at what comes next. After the 3s is the 3p. And so where does it go? After the 3s, it goes to the 3p. P holds 1, 2, 3, 4, 5, 6 electrons. After the 3p is filled up, it has to go to the next lowest one. After 3p, whoops, wrong spot. After the 3p, you can see we go to 4s. And so we go to 4s. That holds 2 electrons because it's just 1 orbital. After the 4s, where does it go? After 4s, it goes to 3d. After 3d, now we're in 3D, so that's going to be this section here. So this is our D block right here. It says it right there. And so D subshells have 5 orbitals. 5 orbitals times 2 electrons each one means it should hold a total of 10 electrons. Let's see if that's true. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now the D block is filled. Where does it have to go? To the 4p. After the 4p, where does it go? To the 5s, then to the 4d, then to the 5p, then to the 6s. And now we have to watch out here because if you look at your periodic table, look at those 2 that are right in this region right here. If you look at them, that should be cesium, element number 55, and barium, element number 56. So cesium here, barium here. Where is 57? If you look at your periodic table, 57 is either going to be written right here or it's written down here, right? Now, where are we going? After the 6s, take a look at our picture here. After 6s, what comes next? 4f. Where's the F block on here? F block's down at the bottom, way down here. And sure enough, what comes after lanthanum, element 57? Well, that's all in the block down at the bottom because that's the F block in here. An F orbital, an F subshell, has how many orbitals? 7 orbitals times 2 electrons each gives us 14 total electrons. And so we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Just like we expect. That's the reason why it's 14 across on the bottom. Then after 4F, we get to 5D. Well, where's 5D? 5D is right here. So we go across another 10 across there, then 6P, and so on and so forth. So I know we've gone into a lot of detail on this, but I just wanted to make it clear to you that this is the reason why this periodic table has this weird shape to it. That the particular shape that it has, that configuration, is because of the fact the electrons fill up subshells from low energy to high energy. If in some other universe is instead of filling up 1s, then 2s, then 2p, it went 2p, then 1s, then 2s, or something like that, which would not be possible. But if it were, then we would expect to see a block of 6 start off the periodic table and then a block of 2 instead of a 2, and then a 6. And it's 2 and 2 and 6 because of the fact it goes S, 2 electrons, S, 2 electrons, P, 6 electrons, S, 2 electrons, P, 6 electrons, and so on and so forth. So it goes 2, then 6, then 2, then 6, and so on and so forth here. So now that we can we know how they fill up, we can describe where all the electrons are in individual atoms. And so the way that electrons are distributed in an atom is called an atom's electron configuration. So that's the term that we'll use. So an electron configuration tells both which subshells have electrons and how many electrons are in each subshell. So at the bottom, this big text down here is an illustration of an electron configuration. Specifically, it is the electron configuration for boron. Boron, if you look at the periodic table, has an atomic number of 5, which means it has 5 protons. If it's a neutral boron atom, that means it also has 5 electrons. Where would those electrons go? As we sort of saw from our previous one, the first 2 electrons are going to have to go into the 1s. Okay? And so as a result, down here you can see we have a 1s. That indicates the subshell, and then how many electrons are in the 1s. We put a little 2 superscript up here to show that there are 2 electrons in the 1s for boron. After the 1s is filled, what do we go to next? The 2s. The 2s is an S, holds s orbitals. It's this s subshell, and so it has 1 orbital because it's an s, and that orbital holds 2 electrons. So therefore, we put the next 2 electrons in the 2s. At that point, the 2s is filled. We still have 1 electron left. We have 4 total, 2 in the 1s, 2 in the 2s. So we need to have 1 more to get to 5. And so where does that go? After it goes to the 2s, it next goes to the 2p. And so how many electrons go into the 2p for boron? Well, just 1, because that gets us up to 5. Notice that, just like we talked about the Aufbau principle, it's filled up the 1s. Then when that happens, it goes in the 2s. Then when it fills up the 2s, when that's filled, then you go to the 2p. And it keeps adding them until they're basically all distributed out into the lowest possible energy subshells. So let's take a look at some examples of these. Hydrogen. Hydrogen, as we said, has just 1 electron, if you look at the periodic table. And so where's the electron going to go? In the lowest possible energy subshell. So it'll be in the 1s. How many in the 1s? Just 1. So the electron configuration is just 1s1. Helium, 2 electrons. First electron is going to go in the 1s because it's the lowest energy subshell. Second electrons also go in the 1s because you can fit 2 electrons into that 1s subshell, because it has 1 orbital, and that orbital holds 2 electrons. So the electron configuration for helium is just 1s2. Lithium, on the other hand, has 3 electrons, and so the first 2 are going to go in the 1s, so we put 1s2, but now it's filled. We can't put a 3rd electron in there because it only holds 2 electrons, because it only has 1 orbital, and that 1 orbital holds 2 electrons. And so the next electron has to go into the next lowest energy subshell, which is the 2s. So we then say 2s1 like this. Look at some more on here. Nitrogen. So nitrogen, if we look at the periodic table, has an atomic number of 7. And so it would be, periodic table-wise, this element right here. And so it has an atomic number of 7. And so it has 7 electrons if it's a neutral atom. So the first 2 electrons would go in the lowest subshell, 1s. So it's 1s2. The next 2 electrons are going to go in the next lowest subshell, 2s2. And there are 3 left over now. They're going to go into the 2p. Does the 2p have room for 3? Yes, it does, because since it's a p subshells, remember, have 3 orbitals. Each orbital holds 2 electrons, so we can hold a total of 6. So if we're doing nitrogen, we'd say 1, 2 electrons in the 1s, 1, 2 in the 2s, so it's 2s2, and then 2p3, so 1, 2, 3 gets us up to nitrogen. So this is the electron configuration of nitrogen. What about sulfur? All right, so let's take a look at what sulfur would be here. Sulfur, if you look at your periodic table, you will see that it has a total of 16 protons, so it has 16 electrons if it's neutral. So we're going to fill them up again. First, so we have 1, 2, and now the 1s is filled, so it's 1s2. 3, 4, so that fills up the 2s. So now it's 2s2. 5, 6, 7, 8, 9, 10, and that's 6 more, which go in the 2p, and now the 2p is filled. Then 11, 12, right there, and so that's 2 more that are in the 3s. That only holds 2, so it's 3s2. 13, 14, 15, 16, and we should be at sulfur. So how many electrons are in the 3p? 1, 2, 3, 4, and so we would finish up with 3p4. Your double check is, of course, just to add up the electrons. 2 plus 2 plus 6 plus 2 plus 4. 2 plus 2 is 4, plus 6 is 10, 12 plus 4 is 16, and that's the correct number of electrons for sulfur. Let's try one a little more challenging. Neodymium, Nd. So neodymium, if you look at your periodic table, is way down at the bottom. It's element number 60. And so that should be, looking at this, I think it's this one right here that we want to go to. And so 60 electrons, we're going to fill them from low to high. First two are in the 1s, so 1s2, 2s2, 1, 2, 3, 4, 5, 6, 2p6, 3s2, 1, 2, 3, 4, 5, 6, 3p6, 1, 2, 4s2, then we go to the 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so 3d10, so then 1, 2, 3, 4, 5, 6, 4p6, then what's next? 1, 2 in the 5s, so 5s2, then what's next? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in the 4D, so 4d10, then we go 1, 2, 3, 4, 5, 6 in the 5p, so 5p6, then 1, 2, 6s2. Now remember this, it breaks down to here, and so now at this point we should have, if you count them over, it's 4f4 because it's actually one of them is going to come from here, and then 1, 2, 3. It's going to end up being 4f4 to make it work out right. So the fact that it actually goes into one of the D beforehand is a little bit of an exception to our normal Aufbau rule, but it's not one that we're going to really focus on for right now. If you ever actually really need to see what the electron configuration is for some of these more detailed elements, the ones that are down at the bottom of the F block and the D block, there are some exceptions because of the fact that these electrons do end up wanting to reach the lowest energy. And sometimes if they get too packed into an orbital or into their orbitals, it'll actually be sort of sometimes less energy for them to spread out a little bit, and that'll throw off the normal Aufbau order that they're in. But for right now, this is going to end with 4f4 because they're 4 going into that 4f energy level or 4f subshell that's right here. And so that would be an example of how you write out a really long electron configuration. Last thing that we have here, if the electrons do fill an atom in the Aufbau order from lowest to highest energy subshells, that atom is considered to be in the ground state, which is a term we've used before talking about energy levels. If a subshell is skipped, even if there are no energy levels skipped, so something like if it went from 1s to 2s, 2s to 3s, where it skipped the 2p right here, then it's considered not to be in a ground state, but instead it's in an excited state. So we don't just have to look at whether energy levels are skipped, we also have to look at whether subshells are skipped, or if basically is that it jumps to a higher subshell before a previous subshell is filled, we say it's an excited state. And so let's look at 3 different electron configurations, all for sodium, and see if they're ground state or not. So for the first one right here, it's 1s2, 2s2, 2p6, 3s1. So first thing, does it skip any subshells? Well, remember our rule here. We have 1s, then 2s, 2p, 3s, 3p, 3d like this, right? And we said the order is 1s, then 2s, then 2p, 3s, like that, and then 3p, and on like this. And so if you notice the order we're in, it's 1s, then 2s, then 2p, then 3s, 1s, 2s, 2p, 3s. So we didn't skip any subshells. The next question we have to ask is, did it fill all the earlier subshells up before going to the next one? Well, the 1s, since it's an s, would hold 2, and it's got 2. The next one is 2s, it's an s, so it holds 2, and it's got 2. The next one is a p, so it holds 6 electrons. Remember, 3 orbitals times 2 electrons per orbital is 6, and it's got 6. And so it didn't go on to our last orbital, the 3s, unless all the other ones were filled. And so because it skipped nothing, it filled up all the lower subshells before it went to the next one. This would be a ground state electron configuration. On the next one, let's look. 1s, then 2s, then 2p, then 3p. So it says 1s first, then 2s is next, then 2p is next, then 3p, oh, not 3p, 3s should go next. So there's a 3s that's missing. It has skipped one of its subshells. And so because of the fact that it jumped to the 3p subshell without having filled up the 3s subshell first, which should be a lower energy than the 3p, this is an excited state because it's lost it there. On the next one here, we have 1s, then 2s, then 2p, then 3p. And so for 1s, 2s, 2p, 3p, it also has skipped an energy level, skipped the 3s. And so as a result, that this would not be a ground state, this would be an excited state. Let me give you one other example. I'm going to modify this last one just a little bit. Let's say we had one that looked like this, 1s2, 2s2, 2p5, 3s1, like this. Excited or ground? Well, the way we can tell is we look at 1, did it skip any? Skip any subshells. So 1s, then 2s, then 2p, then 3s. 1s, then 2s, then 2p, then 3s. Yeah, that went through the right order. And so it didn't skip any subshells. Did it fill all the previous ones before it went to the next one? Well, that 2s is filled, or that 1s is filled, that 2s is filled, the 2p, only has 5. It should never go to the 3s unless the 2p is filled. And since the 2p holds 6, that means this would also be in an excited state down here instead of in a ground state.